back to another video, guys. Got one here for you, which is finding the midpoint. Comes up in a lot of areas. One of those areas are when you're finding the median. And where exactly in the median would you use it? Typically when you have an even amount of numbers and you're trying to find the very center. It's going to lie in between those two. Looking at the diagram here, we have the task of finding the midpoint. The midpoint of -4 and 11, if they're just two numbers out in space, doesn't really have much bearing. I mean, what you'd need to do is get a ruler and then get some sort of measure, split that down the middle. It's no harm in these cases to use the number line. And as soon as the number line appears, we can see immediately, we get a better grip and an idea of roughly where the middle is. And at least a measure of where that is. There's a couple of ways that we could do this. At first, we may think, let's play it safe. Like holding the edge of a swimming pool when it's too deep. Let's just hold on to that side, get some structure, and you know, it may be a bit clumsy, it may be slower than usual, but we're going to get there. And that equivalent here is going to be us counting from the edge. So eventually, once we've counted, and you don't need to use dots, you could use your fingers, we get to the very center. And it's an even call. When we get there, we had an even amount that stopped at 3 and an even amount that stopped at 4. Which means the true center is in between those two numbers. Which we're going to have to find the midpoint. Interestingly, this was the whole point of today's video, is to find the midpoint. How do you find the midpoint of 3 and 4? You probably just know it, right? Because you know in between any two numbers, you just add a half on to the lowest integer. So this point would be 3.5. The absolute diamond question would be, is there any way to have got to that point just knowing the 4 and the 11? The two numbers that we started with. Is there something we could do to those? Turns out that there is. Best way to show that is with some positive integers. So if we had the numbers 5 and 9, what would you intuitively do to find the midpoint of those two numbers? You might seek to find the difference between the two, given here by the 4 in blue. And we know that the difference between them should be halved, split down the middle. Alright, so are you thinking that 2 is the midpoint? A lot of people do, and that's really why I'm saying, well, at least questioning. The fact is, we found the distance that is half of the difference. What we need to do is add that on to the 5. So we finally have the midpoint of 7. I know what you're thinking. Sounds like a lot of work. But this is the point of generalization in maths. Maybe we could find a shortcut, a formula, something that simplifies to be an elegant thing to do instead of do all of this work. Let's take a look at the generalization. So we're going to generalize with the letters L and T. Let's say for the purposes of this example that L is smaller than T. And in the previous example, therefore, L would be a 5 and T would be the 9. What do we do to get that? So, found the difference between the two. And then we halved it. Then we added it on to the smaller number. Okay, We may have a formula, but it doesn't look like it saved us any time. Question we have is, can it be simplified? In order to simplify this, we need to combine the left-hand side with the right-hand side. Now, at the moment, the left-hand side looks like a fraction. Well, it is. And the right-hand side doesn't look like a fraction. Don't know if you've ever really wanted it to be a fraction and thought, well, I'm just going to have it my way. This is how you do it. Any number can be put over 1. You won't change the number, but it's suddenly a fraction. And it's amazing how that starts to open up your creativity and possibilities. To get a common denominator here, we need to match the 2 on the left. So we multiply by 2 on the numerator and the denominator. Just like that. Top and bottom. Now don't be afraid to use a new line so we can show what we just did, but not too much change has happened, so we have less chance to make a mistake. Now, looking at the fraction on the right, you'd think, whoa, let's simplify it. Go ahead. You'll be back where you started, right? So we learn these little things by doing. There's nothing wrong with them. But remember, the focus, the aim here was to combine the left and the right. We can do that now. We've got a common denominator. Let's see what it looks like. First, it doesn't seem like much. But when you realize the only operation on the numerator is a addition or a subtraction, you realize you don't need those brackets and some simplification occurs. So hopefully you can see that the L's are going to combine to give something a lot more simple. If you have negative 1L and we add 2L, we get this. T plus L over 2. Now, you may have seen this result somewhere because a lot of people use A plus B, right? So A plus B over 2. Really showing here that it doesn't matter which letter you use. I'm going to prove the same thing. Now let's try this as a proof of concept on the original question. It's nice also when we confirm the result that we got previously. Just to remind, the midpoint is 3.5. Firstly, we add the two numbers that we have together. That's negative 4 and 11. Then we divide it by 2. Time to add the numerators. And now we have something which we all know is 3.5. What if we want the midpoint of 3 numbers? Let's try and see this working with a real intuitive approach, which is through sharing. Put on the screen here 3. That represents the 3 that we have at the start. If we add all of those numbers together, what we end up with is a total of 20. And this 20 should be then split again so that everyone gets an equal amount. So we now see that the total is 20. We split this into 3 and we get 6 2/3 for each part. So adding them all up into 1 and then sharing them out evenly into thirds will give us the midpoint of all 3. As we mentioned earlier, we see this in something called the mean average. Find it very interesting that the mean average would be a way to represent that group. There's a couple of ways of interpreting that number. You could see it as the most central point of all of those numbers, but it's also got a different meaning that it represents those numbers. Let's say we had 3 numbers from a test score. We want to know which group has done better. If we pick the top, we could compare and say that classroom A had done better. But that person is one person and it does not take into account the others. Which brings about the question, does the midpoint represent a group? Let's take a look at the midpoint of all of those numbers and see what happens. So when I add them all up and divide them by 3, we get these numbers. And it's nothing we're too surprised to see. In fact, the midpoint seems to back it up. Are these numbers just very fortunate numbers? There's no doubt that that is in the center. It seems to be slightly to the left because we have two numbers on the left and only one on the right. That means that it gets dragged about by the proportion numbers that are either side of it. But I wonder, are there a set of numbers, just three numbers, that would make this a totally inaccurate result to consider it for being a representation of those numbers? Let's calculate the middle point of these four numbers now. And just like before, we add them all up and divide it by 4 this time. So we've got 60 divided by 4, and that gives us 15. I don't think we can argue with the fact that 15 is in the middle of all of those numbers. If we now plot this on a number line, the black numbers are the 4 numbers we started with, and the 15 would go right here. That doesn't seem too terrible, but I would question the relevancy of the top number. So looking at this one up here, doesn't seem to be where most of them are. We might call that an extreme value. But from a purely geometric point of view, it makes sense that the X is pulled more to the left because there's more of them to the left, but they still exert some force pulling it to the right and away from that crowd. As soon as we start adding a context to these, we start to see the numbers in a different light. So for the longest time, the mean average has been used to represent the numbers. But let's say that these were the wages of people that were working at a company. Let's say the numbers are different now, and we have a certain number of people on a lower wage, and typically in a company you would have more people on the lower wage doing the low skilled jobs, and less people up at management there with 115,000. Looking at the distribution, a lot of people are down at the bottom, one person at the top. Let's calculate the midpoint of those numbers. Now, turns out that it's 33.4 thousand. If it's an average value, it's meant to represent the average person in that company. Or maybe that's just one way of looking at it. Represents if all of those wages were put in a pot and shared out equally. Does that happen? Oh no. And in a lot of ways, maybe that's good that it doesn't. Although people who are earning less would love the idea, people earning more would not so much like the idea. But the fact is that some jobs are more difficult or carry more responsibility, and so they ought to be paid more in order to drive excellence. So we're not here to reinvent how the world works there, but whether we apply the average to find something out about a company could be, misleading. This 33.4 thousand could be a headline, and if we thought that everyone at that company was on 33.4 thousand, that would look pretty good. You would feel like they were being quite successful. But it's all because of that 115,000 there. If we plot the average, the mean average or the midpoint onto this number line, we can see that it's right in the middle of everything. There's clearly a big bunch of people on the left, and it's nothing to do with them. It's even less to do with the person at the top. But this is the lesson about the midpoint. It does get affected by any number that you add, and the further away from the average, the more it's going to be affected. For example, if I added another point up the top here, you will find that the average would move to the right because there's another number. So it's not just the amount of numbers that are on its right that will add the weight to its movement, it's the farther away that the number is, the more it's going to affect. In the real world, this can be quite dangerous, because if we're going to have large numbers in our data set, it can give us a poor interpretation of the situation. The big number can pull that number really far away from anything that's meaningful. In fact, what would we do in this case? We may even consider those as outliers. It wouldn't really be fair. Since the majority of the company lie down at the bottom there, it might be better to find the average of them separately from the bunch of people that are being paid way too much. So we can see the same concept of midpoints in the coordinate system, because sometimes we don't have a nice straight line that's parallel to a number line. We have diagonals. And how do we find the midpoint? Let's imagine these two coordinates here, and we have to find the midpoint of them. It's not great unless you've got some experience to do this in your head. You probably want to first visualize what's going on. For the purposes of grounding this whole situation on a graph, I'm going to draw these axes, but they're not entirely necessary. All we need to plot is something that's relative. So if we plot 1, 6, 1 across, say about here, and then we go up to 6. Now, you might find it very strange if I write the 6 here, because, well, that should be 6 away in terms of the 1 unit we had down the bottom. It should be a bit further, but actually there's one trick with graphs that does hold, although it does have the ability to skew the data if you're not careful and make it look maybe steeper or less steep, is that the axes units don't need to be the same on the x as they do the y. They just need to be consistent and the same distance apart on each of their own axes. Now, the reason I put 6 here is because I know coming later is 14, and I don't need to have it terribly accurate, but I want it somewhat relative. So we've got our first point just here, and our second point is going to be further up. Now, let's say this is our line, we'll join it up, and we want to find the midpoint of this line. We're looking at the different directions, the x direction and the y direction, which is in the pink. And really useful method for finding the midpoint is to think of it as half of the across and then half of the up. We want to travel only halfway up, approximately here. And a really good way to approach this problem is to think about it as halfway across and then halfway up. If to get to this point at the top, we had to go the whole of the blue, let's only go half. And to go up in the upwards direction, we have to go up the whole way of the pink, let's only go half. And overall, we would have done half of that journey, right? So finding the midpoint is useful here. We're finding the midpoint of 1 and 5. And what are 1 and 5? They're the x coordinates. So let's label them on here with a circle. We want to find the midpoint of the y's in the same way, which would be roughly here. If we look at those numbers, that's going to be halfway between 6 and 14. Labeling those in our coordinates, we have and because when we're dealing with these things, we can't really have more than one of the same thing, otherwise we can't reference it. We're going to give them a little subscript. So the left hand side we'll call the y1, and the right hand side we'll call it y2. Same for the x. Now, how do we find the midpoint of two numbers? We add them together and divide them by 2. So if we focus on the x coordinates first, we can write an expression for the overall end result and do it in one foul swoop. We're in a mega bracket here for the coordinate, and we'll say decent sized comma, and we'll put some sort of formula in here based on x1, x2. So we know that whatever those x values are, we're going to add them together, like so, and then we're going to divide them by 2. That will give us the halfway point of the across direction, the x direction. And then if we do the same for the y, this will give us the halfway distance that we would have travelled before. What does that culminate in? Culminates in us going only halfway up the diagonal. We'll put the actual numbers in and we get this, which is not too bad. And we'll simplify. And I think we're going to have to simplify again. And we finally land at 310, but we have to know if that makes sense intuitively. Let's plot it and see. And yes, it does make perfect sense. 3 is in between the 1 and the 5, and the 10 is in between the 6 and the 14. So we are halfway up our diagonal. So that ends our little journey around some of the applications of finding the middle point of numbers, be it 2, 3 or any more, as well as what it might mean in context and how it's helped us understand situations and groups of people for a very long time, whether you agree or not, because statistics is still massively up for debate, so get involved. Thanks for sticking around, and I'll see you in the next one.